Hello, Eastview scholars. Welcome to this sharp shorts on how to balance a chemical reaction. If you remember from the last video, we just went through, and what we did is we went through this types of reactions, and we started with these are the steps to follow to write and balance a reaction. Well, our last video had us do number one, which was just identify the types, so it can help you understand how to rearrange, because again, we'll go back to it, there's only three types of reactions. You can make something, so create bonds and make a larger compound. You can break something or separate some bonds and break a compound into smaller parts. Or you can rearrange, which means you can break some bonds and then rearrange them and hook different ions to different things. Okay? So that's step one, and we went through that video and named the five types that we're actually going to look at. Synthesis, decomposition, single replacement, double replacement, and combustion. Now what we're going to work on here is, once I identify that, then I need to write the products correctly, and then I need to balance with what are called the stoichiometric coefficients. Or in other words, those numbers that go in front of the compound, not the little subscripts that go behind to balance ionic charges or tell you how many of each element we're sharing, but actually the coefficient out front that in reality, as we're going to learn, tells you how many moles of that substance you need to interact with the moles of the other substance. Anyhow, the only way to do it is to do it. So here I'm going to look at a couple of reactions. I got four separate ones here. This one, I have an element in a compound. That tells me that this is a single replacement reaction. Okay, and I'll just write SR, because that's how I identify it. Now, the other thing I want to do is I want to look, since almost all the time, other than in combustion reactions, we are looking at ionic compounds interacting. We do want to identify what are the separate ions and what are their charges. Is what I want to know with the single replacement. Now, by doing that, I can see that the lithium would want to come in and replace the sodium and bind to the chlorine itself so that I have that positive-negative combination. In a single replacement reaction, if you remember from the video, I have to check and see if lithium is strong enough. So I have to go to my periodic table cheat sheet, look at the list of activity series elements, and see if lithium is higher up on the list. And it is. It is the highest one on the list. Lithium is the strongest in single replacement reactions. So the lithium is going to bind to the chlorine. And all I'm going to do when I write my new products here in step number 2 is I'm going to write down one of each. And then I'm going to worry about is the compound balanced after I get everything written. Because again, I cannot create or destroy matter, so let's make sure we have everything written right. So I have lithium and sodium and chlorine on each side. This came in to bind to the chlorine now as a +1 and a -1. This is now a very happy compound. Okay, because my charge flip-flop, that would be neutralized. Sodium I look at, is that a diatomic element? No, it's not one of the 7 that we have mentioned in our mnemonic paging Dr. Brinkelhoff. Okay, so in all reality, this is okay. Now, step 3 then is I want to be able to balance the equation, which means I can't create or destroy matter. I need to show the exact relationship these things are in. So, let me do a little erasing. At this point then, what I want to do, let me clear some of this out of here. What I want to do then is look and see, do I have the same amount of each element on each side? Well, here I have 1 lithium, here I have 1 lithium. That is balanced. Here I have 1 sodium, here I have 1 sodium. That is balanced. Here I have 1 chlorine, here I have 1 chlorine. So that equation is actually balanced. Now, we don't write them in there, but what that means is each of these has a coefficient of 1. Or in other words, what it's telling you is 1 mole of lithium will combine with exactly 1 mole of sodium chloride to make 1 mole of lithium chloride and 1 mole of sodium. And that shows you the exact relationship that those atoms will rearrange in Dalton's atomic whole number ratios. Okay. Now here I have 2 elements. I'm going to say that that's a synthesis reaction because the only thing you can do with these 2 elements is put them together to create a compound. And again, I might want to just double check and remember that sodium, when it does form an ion, is going to be +1. Chlorine, when it does form an ion, is going to be a -1. So, what I've got here then is I'm going to put down 1 sodium, because the cation is always written first. I'm going to put down 1 chlorine. Okay? Despite the fact that this has a 2 subscript, that is there because chlorine's diatomic and it's covalently sharing 2 chlorines together. That has nothing to do with my new products. One thing to always keep in mind, chemical reactions create new products. What the subscripts do on this side to balance with those elements is not going to be the same over here necessarily. Okay? And then I'm going to check, is a +1 and a -1, that is a happy compound. It is zeroed out. I have created my binary ionic bond. Now is step 3, where I have to balance the left side and the right side. Well, I see I have 1 sodium here, and I have 1 sodium on this side of the arrow in the product side. What I also notice is I have 2 chlorine on the reactant side, but only 1 listed here. This is where the stoichiometric coefficient comes in, or the number in front. Okay. Now I have 2 chlorine on this side and 2 chlorine on this side, but I have to put it out front because it won't work. The sodium and the chlorine are already neutralized when that bond formed with a +1 -1. There's no way I could write this 2 down here because it would throw off the ionic compound, and I can't do that. It would mess it up basically. Now the difference though is anytime I have a subscript, it only affects the thing that's right in front of it. Okay? When I have a stoichiometric coefficient, it affects everything. So that also means that when I put that 2 there to get the 2 chlorine, I now have 2 sodium, so I have to go back to the left side and write a 2 in there. And now it tells me 2 moles of sodium with 1 mole of chlorine will make 2 moles of sodium chloride salt. But it's all balanced. I have the same exact number of elements on each side of that arrow. Okay. Here is 2 compounds, so that's a double replacement reaction. Again, I'm going to identify my cations and anions just so I make sure that I rearrange them properly. I'm throwing the charge down with them too, so when I do form the new compounds, I know very much what's going to happen. So the strontium is going to want to bind with the iodine. Okay. And strontium's a +2 and iodine's a -1, so if I do my charge flip-flop, that's a 2. Okay. Now, calcium is going to want to bind to phosphate. I'm going to write calcium first, because it's the cation, and then phosphate second, that polyatomic second, because it's the anion. Now, this is a +2, that's a -3. I'm going to get my parentheses in place, because when I do my charge flip-flop, I know I'm going to need 3 of these and 2 of those. Now I finished step 2. I've identified my, I've rearranged, and I've made them neutral, as I should in writing a binary ionic or a ternary compound. And now I just have to balance on each side. So I just start 1 element at a time. I have 3 strontium, and I only have 1 here, so I need to put a 3. That gives me 3 times 2 is 6 iodine. So I go back here and I say 3 times 2 is 6 iodine. That gives me 3 calcium also. I had 3 calcium. I have 2 phosphate groups, that's what that coefficient subscript tells me, and I have 2 phosphate groups. I've now balanced this equation to tell me that 1 mole of strontium phosphate combines with 3 moles of calcium iodide to make 3 moles of strontium iodide and 1 mole of calcium phosphate. Our last reaction here is a combustion reaction. Easiest to recognize, I have a hydrocarbon and an oxygen, which means my answer will always be carbon dioxide and water. Okay. They can be the biggest pain in the butt to balance just because they are covalent compounds. They're sharing. Hydrocarbons are covalent. And so, and carbons can share numerous and make very large molecules. So what happens here is your coefficients get to be much larger than they ever would with ionic compounds, because ionic compounds really, other than some transition metals, the largest charge is a plus or minus 3. So those numbers don't get much more than 1, 2, or 3. The trick to doing carbohydrates is start with carbon, then do hydrogen. The last element you try and fix is oxygen, or try and balance as oxygen, because it's the only one in here that's by itself as an element that can kind of be your catch-up moment there. The rest of these are compounds, and any number you put out front is going to affect everything in the compound. So we save that till last, and if it doesn't drop into place right away, it at least tells us where we're going. Anyhow, so I start with carbon. I have 2 carbons, and this is called ethane. I have 1 carbon here in carbon dioxide, so I put a 2. Okay. Now I have 6 hydrogens here. I have 2 in the water, so 3 times 2 will give me 6. Now I count out my oxygens. I have 2 on the left. I have 2 times 2 is 4, plus another 3 in the water, in the 3 waters, is 7. Now, I can see that that leads to a problem already because I have an even number on this side and an odd number on this side. The only coefficient I could put in there to make 7 would be 3.5, and I can't. It has to be a whole number. In a situation like that, what I do is I go back to the hydrocarbon I started with. Now I'm going to do what I call doubling the equation. That coefficient was a 1 before. I'm going to make it a 2. And I'm going to start all over again going through my series. 2 times 2 is now 4, so I'm going to change that number to a 4. Okay. 2 times 6 is 12, so I'm going to take that number to a 6. See what I mean about doubling things? Now what happens then is that number becomes 4 times 2 is 8, plus now that number becomes a 6, as I now have 6 waters, and this number becomes a 14, and I can very easily balance this equation by putting a 7 there. 7 times 2 is 14. So now I have 2 moles of ethane plus 7 moles of oxygen will make 4 moles of carbon dioxide plus 6 moles of water. And if I look closely, I'll see on all of these reactions that I have the same exact number of elements on each side, maintaining my scientific principles of atomic theory. Okay? It takes practice. The more you do, the better, faster, and quicker you become at it. You just have to drill it. It's a language. So drill, 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 and scholar up, Eastview.